Okay, today we'll finish the image preprocessing, okay, for enhancement, equalization, normalization. Okay, last week we stopped here, and actually this is the one I recommended based on the CDF, okay, cumulative density function, okay, up to graph value Z. It almost the best one compared with the previous minimax, or we try to normalize the images so that each image will have exactly the same mean graph value and standard deviation, or we make the total energy sum to unit. Okay, but this one, as I just mentioned before, is because the denominator, the value just or the resulting value is just too small. Okay, very close to zero. So you must be very careful. So anyway, if you have a chance to go for the image equalization, I highly recommend to go for CDF. Okay. Now today I will introduce another very easy. Okay, when I say easy, is the computation is fast. Okay, and it's also very popular used in the display industry. Okay. I mentioned that before, used a lot in the traditional CRT, but it's still used for LCD, even for your smartphone display. Because when you watch the video or the image or anything with your smartphone in a dark room or in a bright room, usually your smartphone will automatically adjust the brightness or contrast, basically by the so-called gamma correction. Okay, gamma correction 这个很有名这个叫gamma 的调整。Okay, nothing to do with the gamma rate or anything, but it just used the notation gamma. Okay, gamma. Anyway, the transformation is like this. If this is F, is the original image, okay, or original graph value, you want to transfer to with another new intensity, okay, of graph value. In the 40, in the diagonal line here, it means you do nothing, okay? The input F will be exactly the same as the output. Okay, when you go for some gamma correction or some function like this, okay, if take x, then if you take x squared, or for the example here, you take the exponential x, then it means what? For a given f, or for a dark graph value, after the transformation, it will become brighter, right? I'm sorry. Let me say it again. For a given f, okay, if you go for the x squared or exponential of x, then the value, I'm sorry. Well, becomes smaller, which means what? If the original image is bright, then it will getting dark, right? But reversely, if we take the square root, okay? The square root of x, or we take log x. Then the same value here, see that? Now, for a given input value f star, then you will convert it into a brighter, right? Into a brighter graph value. But all this function, no matter it's x squared, square root x, or even cube of x or anything, that can be expressed by gamma, okay? Which means we can simply take, now we can let the new value, let me put g here, okay, as the gamma's power of x, okay? Now, and all the function here can be used to represent exponential value of x squared, square root of x, or log x, or anything else. So whenever you change, but for implementation, usually we take the root by 1 over gamma. So when you interpret the result, you must be very careful. You go for this original expression, or we take this one, then the result will inverse, right? Okay. So that's the rule. Okay, that's the final equation. Usually we go for this equation. Now, so let me just show you the. Okay. First, take a look. If the gamma equal to 1.0, which means this is the intensity of the original input. So when the gamma value is getting larger, then it's getting brighter. See that? Okay. If the value is smaller, then it's getting dark. But it depends on how you interpret the gamma correction with this equation or this equation. It doesn't matter. It means whenever you change the gamma value, okay, the intensity will getting darker or brighter. That's it. That's the only purpose for that. Now, the equation is simple, especially for image processing. This is the only equation. I is the intensity, okay? This is the intensity for some pixel. Then suppose the display is 8-bit, so we divide it by 255. In this case, you go for this equation, okay? You go for this equation, 1 over gamma. Gamma here, quick gamma here, okay? Then this value, well, between 0 and 1. Then we times 255, so that we can convert the resulting value between 0 and 255. This is the only, you don't need to use OpenCV to call for the gamma correction function. And you can use that to do it, or you can just simply write a very simple programming code, okay, with this equation. And you need to determine what will be the gamma you are going to use. Here's a magic number. I didn't recommend you use for your own application, but no matter for CRT, for LCD, or for even for your smartphone, usually this gamma value is 2.2, or it will be around 1.8 to 2.2. Okay, the original purpose of gamma correction, because our visual eye, when we look at the image, the transformation is not linear, okay? The transformation of your display is not linear. And somehow, we would like to have some conversion so that the intensity changes can be linear. Okay, that's the only purpose for that. And why 2.2 is based on some human factor analysis by some association. it come up with 2.2 could be the best, okay, best value, so that it can convert the nonlinear, okay, nonlinear intensity changes into a linear with our eyes perception。也就是它原来就是说我这个光的到那个显示器的转换呢，不是线性的。那我们是像我们人在看的时候呢，它是一个线性的。那所以这是人因工程的问题了哈。那anyway， 最后大概假如有机会去看到的值，大概会记，差不多是2.2，这是一个奇妙的值，就是2.2是很常用的。So anyway, if you have no idea about what should be the gamma value, you can always start from 2.2. Okay, and adjust it. Okay, with a smaller value or larger value depends on your application. Okay, that's a so-called gamma correction. Okay, so if you want, you may try out this image, for example, and see what happens. Right? You can input this as the input and see and compare the result with the CDF and see what's going on there. Okay, that's the gamma correction, very popular, especially in the display industry. Okay, even nowadays nobody uses CRT as monitors, but we still need it. Okay, as I mentioned, for your LCD display or even for your smartphone, okay, we still need it. Okay, that's the so-called gamma correction. This is the only equation you need to remember. But always remember, it's based on the power of gamma or the power of 1 over gamma. Okay, you must be very careful. But this usually the final one we use in the programming code. Okay. Okay, gamma. Now let's talk about a little bit about the image smoothing. Actually, your assignment number 2. Okay, mean shift is used for smoothing. Okay, used for smoothing. Okay, the very simple. For this one, we need to design the filter. Okay, we need to design the filter. A filter. Or sometimes called a kernel. Okay. Well, actually, it's a filter is a window. We make it a size of W by W. Okay, for example, the window can be 3 by 3. Okay, 3 by 3. And the window in the center has the coordinate of origin. And its neighbor on the left will be -1 and 0. Okay, and the one on the let me write it here. This will be 0, -1, 0. Okay, and 1, 0. Okay, and this is 0, -1, or 0, and 1. Okay, it doesn't matter. If you put this 1, then it will be -1. That'll be fine. Okay, so that's it. You can define the window. The larger the window size, the better the smoothing. Okay, 视窗越大，它的模糊效果、平滑效果就会越显著。Okay, when you use a large window, which means when you use a very large window, you can remove a lot of noise, but also you will blur, okay, the edges. You will blur or you will lose a lot of the details. So it's a trade-off. Okay, what should be the best window size you are going to use? Okay, once you have this window or you have the filter, then you need to do the, I didn't talk about this yet, called convolution. Well, actually, you know something about deep learning, the basic operation of a neural network model. is convolution. Exactly what we defined here. Okay, the convolution, it goes like this. We input, this is the input, okay? This is the input for an intensity image. Now, I should put on plus J and times the window, okay, the window, or the filter with, okay? And this is for OI and for OJ. This operation is so-called convolution. If you are not familiar with this terminology, it's nothing but the inner product of vectors. 假如你对这种叫玄机哈，对玄机不熟，它这实际上就是内积。If we talk about one-dimensional signal, or when we talk about the vectors, this operation is nothing but the inner product. Okay, exactly the inner product. But because we are talking about the two-dimensional image, so this operation is called convolution. Okay, and I and J are the neighbor. Okay, it divides them. So you need to perform the convolution. So here is your input, and then you need to slide this window pixel by pixel, okay, one by one, throughout the whole image. You know what I'm saying? So the complexity will be in the order of m times n times w squared. Okay, this is the image size. And this will be the filter size. Okay? So you need to do this convolution pixel by pixel, okay? Pixel by pixel throughout. And actually, in deep learning, this filter is learnable. It's learned from your neural network model with some objective, which is called loss function, let's say, okay? But now, for the traditional machine vision, all the window, all the elements here are given by the user, okay? You have to determine what should be the element so that you can smooth the image or you can use it for some very specific application. But when we talk about the neural network, the filter is learned, okay, is learned from your training sample and by updating the model so that you can have the best filter, okay? Let's say, but so far all the elements in a window is given by the user. So now let's go back to the image smoothing. The very first easy one is so-called average filter. Average is nothing but it just, well, actually the filter goes like this. This is the filter with the element, okay? All elements have the value of 1. Then we apply the convolution here, okay? And finally, divided by 9 because the summation of the value is 9. So this is not, this is so-called an averaging. We simply take averaging. You know, in this case, if you have an image like this, for example, and we have some random noise after the normalization, you know, all the random noise point will be gone, right? Because we take the average. But also, you know, for the point here, you will blur the edges of the house, right? Okay, that's, so it depends on what. This is an easy one, but not the best one, okay? besides the average, we can take the so-called weighted average, which means, for example, we can simply take, we have an example here, okay? Here, this window size is 5 by 5, and each one is 5 by 5, okay? And all the values are not equal. They are not equal, the same. Well, if you take the distribution along the x-axis, you can see that 1, 4, 7, 4, 1. It looks like a Gaussian. Okay, it's a Gaussian distribution. And the same here, if you look for the distribution in the y-axis, again, it's also a Gaussian. So which means we can apply a Gaussian filter. Okay, 高斯利波器啊，这个叫高斯利波器。Okay, you know, a two-dimensional Gaussian can be expressed by two Gaussian distribution. Okay, let me say it again. A two-dimensional Gaussian distribution can be expressed by two single Gaussian distribution. So here, okay, this is the equation for the two-dimensional Gaussian distribution. Here, x, y is the location. Okay, it's the location, just like what I'm saying here. In the center, you will have the value of 0, 0, which means x should be equal to 0, 1 will be equal to 0. Okay, and all the other elements, well, you have to input their x value and y value here. Okay. Now, here's a parameter that should be determined by the user, which is sigma, the bandwidth. As you know, if this bandwidth is very large, then you will have what? You might over-smooth the image. When I say over-smooth, which means what? You can remove all the noise point, but also you will severe blurring effect, okay, for the edges, okay? So, there's two factors that will affect the result of smoothing. The very first one will be the window size. Okay, the very first one is the window size. And next will be the bandwidth. Sigma. Okay? If the window size is very large or the bandwidth is also very large, and then you will have, you might get some over smooth. Okay, that could be the problem, so that you have to determine, do you want to use a small window size, a larger bandwidth, or vice versa? Okay, you can do something like this. But anyway, this is the equation. Okay, to design the filter. Now you know how to design the filter, right? Right. The only thing you need to determine is the sigma for the user. X, Y is given by this. Okay, the coordinate in the center have the coordinate of 0 for x and 0 for y. Okay, and what should be, if you go for 5 by 5, what should be the value here? It got to be what? For x. It got to be -2, okay? Got to be -2 and 0, okay? And what about this? Then it will be what? 2 and 0, okay? So x, y are given. It's not defined by the user, but the user need to define what should be the size of the window. That's it, okay? Most of the cases we simply use a 3 by 3, and then you can use 3 by 3 twice. You can smooth the original image to get a smooth image. Then we apply exactly the same filter one more time. Okay, so if you go for two times of 3 by 3, it might be equivalent to one single pass of 5 by 5. They might have the similar effect. 也就是说，你做2次3乘3，可能等同做1次5乘5。 的效果。Okay, I won't say they were exactly the same, but they might have the similar effect for small thing. Okay, so for a lot of different applications, usually we'll fix the window size, but you might have do it twice or 3 times or more. Okay, for different iteration. But anyway, this is the equation. Okay, 有了这个 once you have this Gaussian, okay, equation here, then you will have some fixed, okay, window size like this. Okay, depends on, for this case we use 5 by 5. Okay, and you can select different sigma value. Okay, and then come up with this. And most of the time, you try to use integer. It does not have to be integer, but what is the reason? I mentioned that before. Why usually we lump or we run off or run up or run down the value to integer because the convolution, if the filter is integer because the input is integer, so that we can only carry out the integer multiplication. It is relatively fast compared to the real number multiplication. Okay, that's the only reason why you see only the integer here. But actually, if you go for this original equation, it cannot be integer. Okay, it cannot be integer, but we can round up to the nearest integer number. Okay. So here's this is the original input, okay, and this is the sigma, the bandwidth, the sigma equal to 1, and this sigma equal to 3. See that it getting burned, right? Getting burned when we use a very large sigma here, and we lost a lot of detail. And of course, it could be this may not be a good example because you don't see too much of the noise here, but anyway, that is how it goes. Okay, so always remember, OpenCV will provide the filter for the user to determine what should be the window size and the bandwidth, and it will come up with this window for you automatically. Okay, so that's a weighted average filter. Okay, the weight means. So for each element, it will have different weight, and this is true average. Okay, so which means each element will exactly the same number. Okay. The other, no matter it's a weighted average or averaging filter is linear, the transformation is linear. We can go for some non-linear, okay, non-linear called medium filtering, okay, medium filtering. Okay, for medium filtering, again, you need to determine what should be the window size. You need to determine what should be the window size to use. Okay, and for example, if we go for 3 by 3, okay. I should not say. Okay. Suppose this is our input image. Then if we will go for a 3 by 3, and suppose we have some value. Let me put, the medium means first you need to reorder the number in increasing order or decreasing order rapid form. Okay, suppose we do it in increasing order, so the minimum value will be 5, then 5, and then we have 6, right? Then 6, and then 7, and 8. And 9, and then we have a 210. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we pick up the one in the middle. Okay, so it got to be then will be this value. Okay, this will be the middle. It will be the value in the middle of the sequence. So after that, we convert this value to be 7. Okay, that's so-called media filtering. Okay, everyone follow me. Okay, media. What is the advantage of me? It is an. Did I say it here?
Professor?
Yeah.
I have a question. If the center is the 6, we want to convert to 7. So how can we do it? Plus anything to 1 or rearrange the number?
Could you say it again? I don't quite follow.
Yeah, just.
If this is the graph value in the original image.
And we need to improve the center from 6 to 7. How can we do it? Plus anything with 1 or rearrangement?
No, just assign the new value, the media. You will return 7. You just replace 7 with any value here. It could be any other value. We just replace it. You don't need to do some arithmetic operation. No, not 6 by 1. No, you just replace it because this is the new value. This is the new value. Okay. First, I didn't say it. A media filtering is a nonlinear operation. It's nonlinear. Okay, just not like we calculate the average. Or the convolution here, see that? It's based on linear operation. But when we reorder the value, this operation is so-called nonlinear. Okay? It's nonlinear. And the good thing about it is what? It can preserve the edges, which means we can remove the noise. But at the meantime, you will preserve what? The details. Okay? That is the property of a nonlinear filter. Okay? It's a nonlinear filter. So this so-called edge, here's another terminology called edge. Preserving smoothing. Called edge, which means you can do image smoothing, but at the same time, you will preserve the original edges. Okay? We smooth the noise, but we do nothing for the edges. That's something we want, right? That's something we want. We do want to remove the noise background. But at the same time, if you take a look very closely about the hairs of the model here, see that it still retain or preserve the details, edges. See that? The hair, okay, even the eyebrow, the details is preserved. But for the so-called white noise, or they call a soft noise, and for the dark noise, it called pepper. Okay, pepper noise, 胡椒粉啊，或者像撒盐一样。Okay, we can remove all the noise. But if you go for the average smoothing, you see that all the details might be gone. Okay, you will also not only remove the noise, but also you will blur the edges. Okay. But what could be the disadvantage for the media filtering compared with average? When I say the calculation, and if I use the integer as the element, as I keep mentioning, the calculation of integer is faster than real number. And if you can go for a arithmetic operation, never go for the logical condition. Okay, you don't need to do because for this one you need to do what? determine which value is larger or minimum, right? You need to reorder. So for this case here, it does not go for the arithmetic operation, which means the media filtering will take longer in terms of the computation time. Okay, it's still very fast. Don't worry about it. But compared with the pure mathematical calculation, it still take longer because for this one you need to do some logic adjustment, okay, instead of the calculation. So that's the only, and you need to do that for what? If the image is k by k, again you need to do 1 million times of the 3 by 3 comparison. Okay, it's relatively long compared with the mathematical calculation. But anyway, that is also a very commonly used filter. Okay, so we rank the graph value, okay, in a window in increasing or decreasing order of define, and we pick up the one in the middle as the new graph value. Just replace it. Okay, just replace it. Okay. Now, I would like to say something more. You may not be so familiar with. The previous one is just for image smoothing. We try to remove the line. And now the operation here is try to sharpen. Okay, we do the image sharpen. We try to for example, you might have a bird image, especially for a satellite image, for example, right? You got an image that was transferred from outer space, and the image could be quite blurred. Now, we would like to make the image sharp, okay? The so-called image sharpen, okay? So here, the most easy way to do it is so-called Laplacian filter, okay? Laplacian filter. This notation here is some the double-E guys love to use, okay? Electrical engineering, okay? OPAC means what? Do nothing, okay? OPAC, do nothing. X, retain X. OPAC, which means, because you know the double-E guy, they love to talk about how to handle the frequency, how to handle the signal, right? Okay, when you say OPAC, which means it will retain the original input. The other term is called low pass. Low pass means what? It will pass the low frequency signal. Okay, low means low frequency, 低频的讯号会让它通过。Okay. If we have a 1D, if we go for the low pass filter, then after that, what you got is the signal like this, okay? You will retain only the low frequency signal, okay? And this notation of the subtraction will equal to high pass filter. Means if you go for the high pass filter, it means what? It will only pass the high frequency signal. So after that, this could be the only value that will be retained in the output because it's a high frequency, okay? Low pass, low frequency pass, high frequency pass. That's it. That's the only difference, okay? For implementation, okay? Whenever we talk about the low pass filter, we talk about the average. Okay, we talk about the average in digital image. Whenever we talk about the high pass filter, we talk about the difference. The difference. For example, if the difference of the neighboring pixel, the difference is quite small, right? But when we talk about the difference of the pic here with its neighbor, the difference will be quite large. Okay, so that's the because we are not talking about the continuous world, instead we're talking about the digital discrete world. So whenever we talk about the smoothing, we talk about the average. When we talk about the high pass filter, we talk about the difference. That's it, okay? And we don't care, usually we don't care about the sign. No matter it is positive or negative, we simply care about the magnitude. 好，我们只关心它的量，是正的、负的有时候不重要。Okay, but anyway, image sharpening, we need to apply high pass filter. And a high pass filter is nothing but the all pass filter, which means the X itself, minus the low pass filter. And the low pass filter can be obtained from either here with a Gaussian filter or with average filter, okay? So here. So here's the example here. A high pass filter is the original image, that's all pass, minus the low pass filter. So the original, if we still take it as a window or filter form, for a 3x3 window is okay. In the middle we have the value of 1, or the neighbor have the value of 0, which means we retain the original value. That's it. Okay, and minus the average. Okay, here's the we use a little bit a kind of a weighted average. Okay, it can look like a Gaussian distribution, right? Okay, we put the middle with a larger value of 2, and O is for neighbors with the value of 1. That's it. Okay, so when the minus here, we can, if we know something about the filter, okay, forget the scale here. You know, this exactly is the definition of Laplacian filter. Okay, 拉普拉斯的滤波曲就长成这个样子。Okay, Laplacian filter. Now, or we can calculate the high pass filter like this. Okay, again, this is the all pass filter, which is the original image, and then we simply subtract it from the average. Okay. Then divided by 9, because all the summation of the element here has the value of 9, then the value here, this is another form of Laplacian operator. Laplacian operator. Remember what I just mentioned? For high pass filter, we do nothing but the difference. The difference. See that? We calculate the difference of the center one with its 4 neighbor with minus sign. See that? You calculate the difference compared with 4 neighbor. And this is the same. We retain, okay, we retain the original graph value and compare it with its A neighbors, all with minus 1. So if suppose this, we have an object here, okay? So if you put the window right here, no matter you go for this Laplacian operator or this, okay, A neighbor Laplacian, what will be the outcome value here? Okay, suppose we put, what will be the output? It got to be 0, right? Why is 0? Because the intensity in the middle will be the same as all its neighbor, right? So when you do the subtraction, there will be much the same. So 我在说什么吗？因为你先 suppose we put the window right here, okay, in the background. Here's nothing else. So after the calculation, the value will almost becomes 0. It will be also true if we put the window here, okay, inside the object. Then again, no matter you go for the 4 neighbor Laplacian or A neighbor Laplacian, then no matter the graph value in the middle and always the neighbor's pixel, they were about the same. So when you do the subtraction, the value will be 0. And what will not non-zero? Only around the edges. So after you apply the Laplacian, this could be the result. That's it. It can intensify the edges. Okay. So that's the so-called high-pass filter. Okay, remember a high-pass filter is the original or all-pass filter minus the low-pass filter. The low-pass filter can be average or Gaussian filter. That's it. Okay. Now, another term you need to remember, they all provided by OpenCV called on-sharp masking. Okay, on-sharp masking. Okay. Now, I let you read the details. Okay, but I just show you how it works. Okay, it's the so-called on-sharp masking. Also, it tries to sharp the edges. Okay, to sharp the edges. Here is the general equation for that. We have a parameter called A, which is defined by the user. Okay, I will explain that later on. Now, anyway, here's a parameter A. Okay, A times the original image, which is all pass, and minus low pass. So if A equal to 1 is nothing but 1. If A equal to 1, it becomes original image minus the low pass, which is this one, right? Right? It's nothing but the high pass filter. If A equal to 1, if A equal to 1, 好，叫 A 等于1. Okay? Take a look at this equation here one more time. If A equal to 1, that will be equal to original image minus low pass. In that case, this is the so-called high boost. Okay, high boost. When A equal to 1, the high boost is nothing but the high pass filter. Now, A does not have to be 1. Okay? Now, if A is larger than or equal to 2, okay, that's something we are looking for the so-called on-sharp masking. Okay, A equal to 1 is a special case for high-pass filter. But for this case here, if A equal to 2, okay, A equal to 2, which means equals what? Equal to A equal to 2, A 2 minus 1 is 1. It's nothing but the original image plus what? The high-pass filter. Is equal to, okay, is equal to, okay, A equal to 2, 2 minus 1 is 1, which means it's original image plus the high pass filter. We call high boost. And if A equal to 2 or larger than 2, it's so-called on-sharp masking. Okay, remember the terminology when you use the OpenCV. You need to remember on-sharp masking, and then the code, the function may ask you to input what should be the A value you want to use. Okay, so A equal to 1. Let me summarize one more time. A equal to 1 is nothing but high-pass filter. A equal to 2 or A larger than 2 is so-called on-sharp masking. Okay. So I put it here. Okay, the standard high-pass A equal to 1, but A larger than 1 is so-called high boost, okay, or on-sharp masking. Okay, so let's take a look here again. Okay, then we can take a break. If I put the middle, okay, as the W, okay, as the value, and O is a neighbor with minus 1. So it say if A equal to 1, A equal to 1, what? It's 9 minus A, then W will equal to A. Again, it's nothing but a Laplacian filter, right? A neighbor Laplacian filter, right? But if A larger than 1, for this case here, we simply assume A is 10 over 9, okay? Then W will equal to 9. So it is larger than 8. Then in that case, we put 9, okay? We put 9 here, then it's called on-sharp masking, okay? On-sharp masking. It's not A. Okay, if equal to A, it's nothing but a high-pass filter. But if A larger than 1, then it's so-called on-sharp masking. It does not have to be to be 1 or 2 as long as it's larger than 1. Okay, that's the what we define the unsharp masking. Okay, so all the remaining equation will be the same. Okay, let's take a break. Okay, then I will show you how it works. Okay, with one-dimensional signal. Okay.